Hello, I'm John Perdew, and I would like to tell you about the basics of ground state density functional theory. This is a variant of a tutorial that I give at the APS March meeting every other year. Let's start with some of the questions that we get asked about the ground state electronic structure problem for atoms, molecules, and solids. For instance, what atoms, molecules, and solids can exist and with what properties? What are the ground state energies E, the ground state energy differences delta E, the electron densities N of R, or spin densities N up and N down? What are the nuclear vibrational frequencies? How much energy is needed to remove electrons or to break bonds? These questions are answered by electronic structure theory in general and by density functional theory in particular. There are two first principles approaches for materials prediction. The correlated wave function theory, which has the motto, the right answer for the right reason. Unfortunately, that often comes at great cost and mainly for small systems with few electrons. And the density functional theory, whose motto is almost the right answer for almost the right reason at almost the right price for almost all systems of interest. There are a lot of almosts there. So this tutorial will present the logical and mathematical structure of correlated wave function theory and density functional theory. It will explain why both theories are needed. For instance, density functional theory is rooted in correlated wave function theory. And correlated wave function theory also provides accurate and computationally expensive benchmark energies and densities for few electron systems. So it provides reference values against which we can test the accuracy of approximate density functions. So I will have a separate research talk which will explain how density functional approximations are developed. And in particular, it will focus on the highly predictive SCAN functional. SCAN is an acronym for strongly constrained and appropriately normed. It will also present some of the physical applications of density functional theory in general and SCAN in particular, with a focus on symmetry breaking and how symmetry breaking can describe strong correlation in density function theory. Let's begin by asking how widely used density functional theory is. This is a question that you could answer yourself if your library has a subscription to the Web of Science. You could look up the number of articles published in the last 50 years that mention a particular topic. When I did this, for the topic quantum mechanics, I found 56,000 papers. For the topic quantum theory, I found 177,000. But for the topic density functional theory, I found 351,000 papers published in the last 50 years that mention that topic. And the gaps between these three numbers are still growing, but in fact, there's only one density functional theory Nobel Prize that went to Walter Kohn in 1998. So let's start with the correlated wave function theory. We have to begin with a Hamiltonian, and I'm going to write down a non-relativistic Hamiltonian operator for a system of n electrons. Each electron has a label I, and I runs from 1, 2, up through n. N electrons in the presence of a scalar external potential V of R. This is just a multiplication operator, which is a function of position. And the Hamiltonian operator for this system is the sum of three terms. First, there's a kinetic energy operator, which is the sum of the separate kinetic energy operators for each electron. Then there's the electron-electron Coulomb repulsion, which is sum over pairs of electrons, I and J. In the sum, we have to exclude the J equals I term because an electron does not interact with itself. And because the pair IJ and the pair JI are the same pair, they're double counting in this sum, and we have to correct it by dividing by 2. The external potential V of R in this problem can be any function of position, but in most problems of interest, it's actually the electron nucleus Coulomb attraction, which is also an attractive Coulomb interaction between each negatively charged electron and each nucleus with a positive charge Z beta. Typically, we add another term to the energy, which is the nucleus-nucleus Coulomb repulsion. But this we don't normally treat as an operator because the heavy nuclei are typically treated in density functional theory as slow-moving classical particles or even as particles at rest. The Schrödinger equation generalizes from one electron to many electrons. It's an eigenvalue problem for the n-electron Hamiltonian. The eigenvalues are the possible total energies of the system, and the eigenstates, capital psi, are n-electron correlated wave functions. Those wave functions are functions of the position and Z component of spin for each of the electrons 1 up through n. So the wave function is a function of many variables, and that makes it a complicated object. Now, once we have the total energy E, we can find energy differences delta E simply by changing the external potential or changing. The wave function, the n-electron wave function is normalized so that its scalar product with itself is equal to 1. It also has a probability interpretation like the one electron wave function. The wave function is also anti-symmetric because electrons are fermions. That means that if I interchange the labels of electron, the positions and coordinates of electron I and electron J in the wave function must change sign. And the only physically allowed wave functions are, in fact, anti-symmetric ones for electrons. So the only solutions of that Schrödinger equation that are physically meaningful are the anti-symmetric solutions. Once we have the many electron wave function, we can get the electron density from it. The electron density is n of r. It's just a function of one position coordinate in 3-dimensional space, which makes it much simpler than the wave function. And we get that by squaring the n-electron wave function, multiplying by n, summing over the z coordinates of all of the spins, and integrating over the position coordinates of electrons 2 through electron n, while setting the coordinate of position 1 equal to r, the argument of the density. And I think you could see that if you now integrate this electron density over 3-dimensional space, you will just get the number of electrons n. And that's because the wave function itself must be normalized. Now, what is a functional? A functional is a mathematical rule that assigns a number like h to every function like psi. And in wave function theory, we can define an energy functional, h of psi, which is the expectation value of the Hamiltonian, of an n-electron Hamiltonian using an n-electron wave function. And the Schrödinger equation can be derived from wave function variational principle which says that the extrema of this energy functional h of psi over all n-electron wave functions are the stationary states of the system. The extrema could be minima, they could be maxima, they could be saddle points. They're places where the first derivative is zero. The absolute minimum of this energy functional is the ground state. The wave function, that's the ground state wave, is achieved by the ground state wave function and the ground state energy. And the energy E is a Lagrange multiplier for normalization in this minimization problem. So correlated wave functions can be very accurate, but they're never used for a large electron number because the computational cost is prohibitive. Now, why is that? Why not use many electron wave functions for large systems? Well, I'm going to give you an argument that comes from Walter Kohn's 1998 Nobel lecture. Suppose that we decide to compute and store the wave function on a grid of points. Each electron has lives in its own three-dimensional space, so to speak. So let's say we put m points in three-dimensional space for each of the n electrons. Then to compute and store the wave function, we have to compute and store m to the n numbers, because we have m values for the position of electron 1, we have m grid points for the position of electron 2, and so forth, so on, up to m grid points for the position of electron n. That makes m to the power n. To see how this works and how rapidly m to the n increases with n, let's take m to be 1,000 or 10 to the 3. That's not really enough for any realistic problem because it only puts 10 grid points along each of the three dimensions of 3D space. But it tells the story. Now, if we have a 2-electron system, n is 2, and m to the n is 10 to the 3 to the power 2, which is 10 to the power 6. And that's practical for computers can compute and store a million numbers. But if we have 10-electron system and n is 10, then m to the n is 10 to the 3 to the power 10, which is 10 to the power 30. That's not practical for computers. Computers cannot compute and store that many numbers. So it seems like we can't even do 10-electron system with wave function theory, but that's not quite right because quantum chemists don't really use grids. They use basis sets. And with these basis sets, they can study at great expense up to maybe 100 system of maybe 100 electrons with a many electron wave function. On the other hand, the density, n of r, would only require computing and storing m equals 10 to the 3 values in this example. That shows you the computational advantage of using the density instead of the wave function, if possible. Because the density is a low-dimensional system. It just lives in a 3-dimensional space, and the wave function lives in a 3n-dimensional. If we want to use the density, we have to show that we can use it. And the Hohenberg-Kohn theorem from 1964 shows that that is indeed possible. This is the central theorem of density functional theory. The Hohenberg-Kohn theorem consists of 2 parts. And the first part says that there exists a functional f of n of the electron density, such that the ground state energy and density for n electrons in the presence of external potential V of r is found by minimizing over all n electron densities n of r the sum of 2 terms. One term is is functional only of the density. That's the f of n term. The other term is an integral over the three-dimensional space of the external potential V of r times the density n of r. That's a function of the external potential and the density. A physical problem is defined by a fixed external potential V of r and a fixed number of electrons. So the minimum is taken over all positive densities that integrate to a given number, capital N. And this functional f of n is asserted to be universal, i.e. it's independent of the external potential. And if this theorem is true, then the remaining problem is just to find f of n and minimize it, or in practice to construct a good approximation for it. Let me show you the proof of the first part of the Hohenberg-Kohn theorem by Mel Levy's constrained search from 1979. The original proof of this theorem by Hohenberg and Kohn in 1964 wasn't really quite general enough because it had to assume that the ground state of the system you're interested in is non-degenerate. Levy's proof doesn't have that restriction. And it has a further advantage that it's a much more intuitive proof, which actually shows you what all the functionals are. Even though you may not be able to compute them all, you can understand mathematically what they are. What Levy did is to start with the wave function variational principle that I just talked about. The ground state energy is the minimum over all n-electron wave functions of the expectation value of the Hamiltonian, the n-electron Hamiltonian, using that wave function. And do the search over wave functions in two steps. The first or inner step is a minimum over all the n-electron wave functions that yield a given n-electron density n. And in general, there can be many such wave functions that yield the same density. The second step is to do the minimum over all n-electron densities. And when you look at it from this point of view, you can see that it's equivalent to simply minimizing over all the n-electron densities, a functional of the density plus the integral of V of r n of r. And that's because when we compute the expectation value of the external potential for any wave function that has the density n of r, we always get the same answer, integral over three-dimensional space of V of r times n of r. So that proves the Hohenberg-Kohn theorem, and what's more, it shows us what the universal Hohenberg-Kohn functional is. It's the minimum over all wave functions yielding a density n of r of the expectation value of kinetic energy operator plus the electron operator. If we take one of those wave functions that minimum produce the minimum and call it psi n, then f of n is psi n t plus dE psi. Psi n is that wave function, or one of those wave functions yielding a density n that minimizes the expectation value of t plus d. The second part of the Hohenberg-Kohn theorem asserts that the external potential V of r, it has to be a scalar external potential, and hence the Hamiltonian, are determined with an additive constant by the ground state density n of r. So if you know n of r, you can certainly integrate it to find the number of electrons. But you can also find V of r from n of r, and the proof of that goes through the Euler equation for the ground state density n of r. So we have to find an extremum or a minimum in this case of the functional f of n plus the integral of n times b, subject to the constraint that the integral of n is a fixed constant capital N. So we introduce a Lagrange multiplier mu to enforce that constraint. And then we can look at an unconstrained first variation of f of n plus the integral of nv minus mu times the integral of the density, and set that first variation to 0, as it should be at a minimum or an extremum. Then we can find from that the equation for the density, which the Euler equation, which says that the first functional derivative of f with respect to the density n of r, which I'll define in a minute, plus the external potential v of r minus the chemical potential mu is equal to 0. You can algebraically solve that equation to find v of r equals mu minus functional derivative of f with respect to n of r. And that proves this, the second part of the Holmberg-Kuhn theorem, because mu is just an additive constant and DFT n of r is just a functional of r and a function of position. Now, what is this functional derivative? How do we define DFT n of r? Well, it's straightforward in principle. If you make an infinitesimal variation of the density, let's call that delta n of r at each point in space, that should lead to an infinitesimal change in the functional f of n, assuming that the functional is continuous. The relationship between delta n and delta f should be the relation that's shown here. Delta f should be an integral over the three-dimensional space of some function of r that we call the first functional derivative times delta n of r. Now, sometimes functional derivatives are not so easy to evaluate, but they're always easy to evaluate when the functional is local. So let me give you an example. The local density approximation for the exchange energy, it says the exchange energy for a density n is a negative constant times the integral over the three-dimensional space of the density at r raised to the 4/3 power. If we make a first variation of the density, an infinitesimal variation of the density, then this integral becomes what you see on the last line. And this is now in a form where you can identify the functional derivative. So the functional derivative of ex LdA with respect to n is minus 4/3 c times n to the 1/3 of r. And that is a quantity that in the Cohen-Sham theory we'll talk about later, serves as a local density approximation to the exchange potential, the effective exchange potential that electrons see. Notice that it's just a function of r. It's not an operator. It's just a function of position. The functional derivative is always just a function of r. I want to stress that the Levy-constrained search is for understanding. It's not for calculating. The exact universal functional f of n requires a constrained search over n electron wave functions. And that's actually more expensive than solving the n electron Schrodinger equation. If we approximate f of n with an explicit functional of the density, we typically find that although we can do that, the approximations are not accurate enough to be very useful. They give us some very general information about the energy, but they are not accurate enough to be helpful, to help us understand experiments. Now, in 1964, Cohen and Sham introduced a solution to that problem by introducing spin orbitals or one electron wave functions, which are also called Cohen-Sham orbitals. And in their approach, the density n is constructed from these Cohen-Sham orbitals, and the biggest part of the Hohenberg-Kuhn functional f of n is also constructed correctly from the orbitals. There's still a smaller part left over, the exchange correlation energy, which has to be approximated in Cohen-Sham theory. I think that's unavoidable. That's the many body part of the energy, and I don't think we'll ever have a calculable exact expression. But we can make approximations, and we can make the approximations better and better as time goes on. When I say that this exchange correlation energy is small, I don't want to say it's unimportant. In fact, it's very important because it's nature's glue. The exchange correlation energy is what binds one atom to another to make a molecule or a solid. That's typically what we want to understand in the electronic structure problem. If you leave out the exchange correlation energy or set it to 0 in a Kohn-Sham calculation, you find that molecules and solids are either unbound or they're just barely bound, not realistically bound at all. So in Kohn-Sham theory, we posit a fictional non-interacting system with the same ground state density as the interacting system. In this non-interacting system, the electron-electron interaction, VEE, is set to 0. As a result, the Hamiltonian of that system is just the sum of a kinetic energy operator and the sum of the interactions of each electron, the sum effective potential ds of r, which is in general different from the external potential that the non-interacting electrons see. But the important thing is that this Hamiltonian is a sum of one electron terms. It doesn't have any pair interactions in it, only it's just purely a sum of one electron terms or single electron terms. The S actually stands here for single particle. It's not a single particle system, it's a system whose Hamiltonian is a sum of single electron terms. We can solve the n-electron Schrodinger equation for this non-interacting Hamiltonian to find non-interacting energies and non-interacting wave functions. Here, phi n is that non-interacting wave function that yields the density n of r and ground state density n of r and minimizes the expectation value of just the kinetic energy. You can get that by going back to the Levy constrained search and setting the electron-electron interaction operator to 0 from the very beginning. It follows from what we already did. Now, the nice thing about this exact Kohn-Sham theory is that it allows us to write down exact expressions for every term in the ground state energy as functionals of the electron density. And that starts to be done on this slide. For instance, the non-interacting kinetic energy Ts of n is simply the expectation value of the kinetic energy operator using the non-interacting wave function or single Slater determinant that yields the density n. The Hohenberg-Kohn functional for the interacting system was defined before to be the expectation value of T plus VEE using that wave function that yields the density n and minimizes T plus VEE. And we'll simply define a Coulomb correlation energy EC by setting that Hohenberg-Kohn F of n equal to the expectation value of T plus VEE using the non-interacting wave function plus a correction, which is the Coulomb correlation energy EC of n. If we solve for EC of n in the second equation, we get the third equation. The Coulomb correlation energy is just the difference between two expectation values of T plus VEE. The first expectation value is taken using the interacting wave function that yields the ground state density, yields the density n. And the second term is uses the non-interacting ground state wave function that yields the same density n. And if you look at that expression and think about it for a minute, you'll see that the Coulomb correlation energy must always be negative or 0. It can never be positive. And that's because psi n is the interacting wave function that yields the density n and minimizes T plus VE. So the first term, it must be lower in energy than the second term, which means the difference must be negative or 0. We can also define a Hartree electrostatic energy U, which is the classical interaction of the Coulomb interaction of the electron density with itself. This is a quantity that appears frequently in classical electrostatics, for instance. We simply introduce it here because it contains a lot of the correct physics, but not all of it. And because it's an explicit functional of the density. It's a non-local functional, U is a non-local function of the density, but it's still a functional of the density that we know. So now we can define the exchange energy, dx, for density n, by starting from the expectation value of the electron-electron operator using the non-interacting wave function for density n, and setting that equal to the Hartree energy plus the exchange energy. And in fact, one can show that the exchange energy is always negative as well. And finally, we'll define the exchange correlation energy as the sum of the exchange energy and the correlation energy. Then we have everything we need to write out the Hohenberg-Kohn, the universal functional f of n as a sum of three terms. Ts of n is the non-interacting kinetic energy defined on the preceding page. U of n is the Hartree energy defined there, and exc of n is the exchange correlation energy defined there. We have exact expressions for all these things, and as you will see when I just in another slide or two, we can compute Ts of n exactly using Kohn-Sham orbitals. We can compute the Hartree energy exactly using the density. And the only quantity that remains to be approximated is this many-body exchange correlation energy, which in fact, I believe always has to be approximate in practice to get something that's computationally feasible. So how will we find these this non-interacting system? How will we find the potential Vs? How will we find the Kohn-Sham spin orbitals and so on? Well, we have to remember that we have an interacting system and a non-interacting system that by hypothesis have the same ground state density. And if we write out the Euler equation for that density, there are different equations. The equation in the non-interacting system is the first and simpler one on this page. That involves just ds. And the Euler equation in the interacting system that involves the true external potential V of R is the equation below it. And because these two solutions have to have the same ground state, have to be the same ground state density, these equations have to be the same equation in some sense. And in particular, we can find that Vs of R must be equal to V of R plus the Hartree electrostatic potential, which is the classical Hartree electrostatic potential, which is the functional derivative of U with respect to n of R, plus an exchange correlation potential, which is the functional derivative of exc with respect to n of R. Notice again that every term in that potential Vs of R is just a function of position, and not otherwise an operator. It's not an integral or differential operator. It's just a multiplication operator. So now I want to show you the self-consistent one-electron equations for the Kohn-Sham orbitals that see the effective potential Vs of R. Since it's a non-interacting system, these are just one-electron Schrodinger equations. That's the beauty of the method because it replaces the many-electron Schrodinger equation by the much simpler one-electron Schrodinger equation. A particular Kohn-Sham orbital psi alpha of R has a one-electron Hamiltonian, which consists of a one-electron kinetic energy operator, the external potential, the Hartree electrostatic potential from the total electron density, and the exchange correlation potential at position R. In a non-interacting system, we can find the ground state total energy by summing up the squares of the occupied Kohn-Sham orbitals. And since this is supposed to be the ground state of this non-interacting system, the occupied orbitals should all lie below the chemical potential, and the unoccupied orbitals should all lie above it. That's a simple version of the Pauli exclusion principle. Occupation numbers 1 below for energies below the orbital energies below the chemical potential and 0 for orbital energies above. Now, solving this equation is not immediate because it's a self-consistent equation. In order to find the density, you have to find the orbitals. To find the orbitals, you have to know the density. In fact, the chain is something like this. If you knew the complete set of Cohen-Sham orbitals indicated by the curly bracket, you could immediately construct the density by the second equation on this slide. From the density, you could construct the effective potential Vs of R by the first equation on this slide. Then you could solve that first equation to find the orbitals by the first equation. Doing that, of course, requires an iteration to self-consistency. You guess a set of Cohen-Sham orbitals or a density to start with, and then you go through this procedure and you get a new set of orbitals or a new density. You mix the fraction of the old solution with the complementary fraction of the new solution, and you keep iterating until your numbers stop changing at the level that you regard as a level of convergence. So the energy and the density should be well enough converged that you reach self-consistency. Then you stop. And you have the density, you have the orbitals. You can also find the energy. For instance, the non-interacting kinetic energy for that density is simply the sum. It's simply the sum over all the occupied orbitals of the kinetic energy of each orbital. And these Cohen-Sham spin orbitals are implicit functionals of the density, because if you know the density, you can find them by solving the first equation. Can anything go wrong in the Cohen-Sham theory that I've shown you, the exact Cohen-Sham theory that I've shown you so far? Well, something could sometimes go wrong, because the ground state wave function of the interacting system could have a density that's not the density of any non-interacting ground state wave function. It would still, however, be the density of a non-interacting ensemble of a statistical mixture of non-interacting wave functions. So we can avoid any formal problem very simply by redefining the constrained search, so that instead of searching over n-electron wave functions, we search over n-electron ensembles of wave functions. And in this case, the occupation numbers could come out fractional. If there are degenerate Cohen-Sham orbitals at the Fermi level, they could have fractional, and not 0 or 1. The theory that I've shown you so far is the total density functional. And in fact, it's rigorously true as long as the external potential doesn't depend on the spin. As long as the external potential is the same for all the electrons, then you can, in principle, use the total density in an exact Cohen-Sham theory. You can also go through the Levy constrained search and replace the density n of R by the up and down spin densities n up of R and n down of R, which together add up to give you the total density n of R. You could even have the external potential be different for the up spins and the down spins. And you could make a spin density functional theory, an exact spin density functional theory, in exactly the same way that you made a total density functional theory. It turns out that this generalization is useful even when the external potential is independent of the spin, which is the usual case, because the external potential usually is a Coulomb interaction of electrons with nuclei. And even in that case, if you make an approximation for EXC, you get better results from that approximation applied to the separate up and down spin densities than for that approximation applied to the total density. And there's a simple explanation for that. It's because two functions, n up of r and n down of r, provide twice as much information as one function n of r provides. And the extra information can be used to make the functional more accurate, approximate functional more accurate. Okay, so now you've seen the Kohn-Sham theory, the Kohn-Sham equations. These Kohn-Sham self-consistent equations are implemented in many computer codes. That includes the open source codes that you can get for free on the web, and also the commercial codes that you have to buy. There are many such codes that are written to implement Kohn-Sham theory for molecules or solids or for both. Some codes can do both. These codes can also describe defects in solids, such as atomic vacancies. They do that by supercells. So you create a periodic solid which is built up of large supercells that contain many atoms, and you can put one vacancy in each supercell. And if the supercell is big enough, it's like studying an isolated vacancy. You could also use Kohn-Sham theory to study liquids, like liquid water via ab initio molecular dynamics. The Kohn-Sham energy, the derivative of the Kohn-Sham energy with respect to the nuclear coordinates provides a kind of force that on which you, first principles force on which you can do molecular dynamics to move the nuclei around under the influence of Newton's second law. So these, this Kohn-Sham method and the codes that implement it are our principal source of information about ground state energies, ground state energy differences, ground state electron densities and spin densities, the geometric structures of molecules and solids, the phonon frequencies, and also in many cases about one particle properties. Even though the first one particle properties are not exact even in the exact Kohn-Sham theory. And the one that one would most like to have exact is, in fact, the fundamental band gap in an insulator or a semiconductor. Even the exact Kohn-Sham theory does not predict the exact fundamental energy gap of a solid. There's a subtle reason for that, because the energy gap is actually a difference of ground state energies. But the exact gap is not predicted by the exact Kohn-Sham band structure, because when you change the electron number, the derivative of the energy with respect to electron number changes discontinuously. Anyway, if instead of Kohn-Sham theory, you use a generalized Kohn-Sham theory, in which the exchange correlation functional depends explicitly on the orbitals, and the exchange correlation potential is then a differential or integral operator. That approach can, in principle, yield exact gaps. And in fact, with hybrid functionals and self-interaction corrections, one can get fairly accurate gaps even from approximate functionals, but only in generalized Kohn-Sham theory, not in the original Kohn-Sham theory. Okay, so now I'd like to discuss the exact constraints. We have exact expressions for the exchange energy as a function of the density and the correlation energy as a function. I showed you some of those exact expressions on earlier slides. Because we have exact expressions, and because the Coulomb repulsion between electrons is very simple, it's just 1 over r. We now know about 20 exact mathematical properties of the density functionals for the exchange and correlation energy. And these mathematical properties include equalities, scaling relations, bounds, limits, and so on. On the exchange energy, or on the correlation energy, or on the sum of the two. Now, some of these mathematical conditions are satisfied by all widely used approximate functions. And I claim that the more exact constraints that an approximate functional satisfies, the more widely accurate and predictive it can be over the vast material space. the space of possible molecules and materials is truly vast. I think it's an infinite space. And a functional that works well over this vast space needs to be very sophisticated. It needs to know as much as it can about the exact function. And by satisfying the exact constraints, we can make the functional more predictive. You can read about this. You can read about all the exact constraints and how they are used to construct functionals in the paper that's mentioned in green below on the bottom of the slide. It's by Aaron Kaplan, Mel Levy, and myself. It's called The Predictive Power of Exact Constraints and Appropriate Norms in Density Functional Theory. It will be published in the annual reviews of physical chemistry soon, I believe, but it's also available on the archive. The archive number is given here. 2207-03855B. I'm going to give you an example of an exact constraint. This is the uniform density scaling property of the exact density functional for the exchange energy. This property was derived by Levy and Perdew in 1985, and it's satisfied by the local spin density approximation and by nearly all approximate functionals that have ever been proposed. And there are hundreds of approximate functionals that have been proposed over the years. Some of them more empirical, some of them more non-empirical, but almost all of them satisfy this constraint by construction. And here's what it says. If we have any density n of r, we have any positive scale parameter gamma, that's just a positive number. And if we have any arbitrary origin for R, we can define a scale density n gamma of R, which is defined to be gamma cubed times n of gamma R. When you do that kind of density scaling, you leave the electron number unchanged, as you can see by simply integrating n gamma over the three-dimensional R space. You'll get the same number as you get by integrating n of R over that space. And the scaling relation says that the exchange energy, EX, the exact exchange energy for the scale density n gamma is equal to the scale parameter gamma times the exchange energy of the unscaled density. Now, to make that even clearer, I'm gonna think about a very physical example. Suppose we have one electron ion with a nuclear charge, capital Z. We know that the solution of that problem is a hydrogenic solution. The ground state is an exponential one electron wave function. Let's put the nucleus at the origin, and then the density will scale as you see in this figure. For instance, for Z equals 1, you just see the exponential hydrogen density. For Z equals 5, you see the density of boron plus 4, which is much more localized near the origin and falls off much faster than the hydrogen density. I also show as Z equals 0.5 to show that mathematically you can scale toward in either direction, even though physically you can't make a nuclear charge of 0.5. In this situation, the exact exchange energy for nuclear charge Z scales like Z. This is a more general result, but that's a specific example. Now I want to take you through the first 3 rungs of Jacob's ladder of density functional approximations. This is a classification scheme for density functional approximations. And the lowest rung is the local spin density approximation, which was made by Cohn and Sham in 1964, 65, I guess. The input for that we like to use for this one is the Perdew long 92 input. The LSDA exchange correlation energy is a functional of the up and down electron spin densities It's a single integral over the three-dimensional space of the total electron density n of r times the function epsilon x c uniform of n down of r and n up of r. And that function is chosen to be the exchange correlation energy per particle in a uniform electron gas that has uniform spin densities n up and n down. So the LSDA is designed to be exact for all uniform spin densities, all systems of uniform spin densities. It's also very accurate for systems in which the spin density varies slowly enough over space. It turned out to be usefully accurate. It's actually more accurate than the Hartree-Fock approximation for most of the properties of molecules and solids. So it turned out to be a big advance. The second rung of the Jacob's ladder are the generalized gradient approximations, where we still have a single integral over three-dimensional space. We still have the total electron density as a factor. And then we have a function, which is a function not only of the up and down spin densities, but also of their first gradients. And that is chosen to bring some inhomogeneity effects into the functional to make it correct away from the uniform density limit to some extent. An example of a generalized gradient approximation that's constructed non-empirically is the Perdew-Ernzerhof GGA. The GGAs achieve considerable improvement for the properties of molecules and solids over LSDA, but it's still not really enough of an improvement to be satisfactory. So we go to the third one, where we have a meta-generalized gradient approximations. An example of this would be the scan meta-GGA, which I'll talk about more in my research talk. We still have an integral over a three-dimensional space of n of r times a function of r. And so that means that this is still semi-local. But the function of r now depends on even more ingredients, not just the up and down spin densities and their gradients, but also tau up and tau down, where tau sigma of r is the positive non-interacting kinetic energy density, which is simply the sum over the occupied Kohn-Sham orbitals of 1/2 the square of the gradient of each Kohn-Sham orbit. You can get that by starting from a more familiar expression for the kinetic energy density and doing a simple integration by parts. It's not so obvious right away why tau is a natural ingredient of the functionals, but it is, and I'll talk more about that in my research talk. So these are the first three are semi-local rungs of the Jacob's ladder of density functional approximations. The ingredients added on each rung make it possible to satisfy more exact constraints, or if you prefer, to fit data better. The local spin density approximation inherits 9 exact constraints from its uniform gas appropriate norm. We know the exchange correlation is a particle of a uniform electron gas from accurate quantum Monte Carlo calculations by Separately and Alder. And simply by being right for the uniform electron gas, LSDA satisfies 9 of the 20 known exact constraints. The PBE-GGA is constructed to satisfy 11 exact constraints, so it builds in a little more constraint information. And the scan functional is designed to satisfy 17 exact constraints. Actually, all of the exact constraints that can be satisfied on the first 3 rungs of the ladder are satisfied here. Ladder also has the 4th and 5th rung, which includes fully non-local functionals like the hybrids of semi-local functionals with exact exchange and the self-interaction corrections on the 4th rung. And on the fifth rung, we have RPA-like functionals that use not only the occupied cone sham models, but also the unoccupied cone sham models to construct the correlation energy. So as we climb the ladder, the functionals can become significantly more accurate and predictive. More accurate because they have more ingredients, and more predictive if those ingredients are used to satisfy as many exact constraints as possible. The functionals also, of course, become more computationally expensive, but the increase in computational expense from the first to the third rung is only a factor of 3 or 5, something like that. It's not a big computational increase for a big increase in accuracy. So I'd like to summarize my talk now. First of all, so this is a tutorial talk about density functional theory. First of all, density functional theory is rooted in many electron wave function theory. Constrained search tells us, for instance, how to go from the wave function variational principle to the density variational principle. Density functional theory is less accurate than wave function theory, but more computationally efficient for systems that have many electrons. And in fact, DFT is much more widely used than wave function theory, although both are widely used. Density functional theory has a rigorous underlying exact theory. That's the theory that I showed you in this talk. It's exact for the ground state energy and the ground state density of any system in principle. And the existence of this exact theory motivates the search for continuing improvements in the approximations for the exchange correlation energy. If you know that something exists and is important, you're motivated to look for it, to look hard. So many people have been working hard on this problem for a long time and making a lot of progress. More progress can be made. We are certainly not at the end of the line. Finally, the approximations can become more accurate and predictive over time, but also more expensive by satisfying more exact constraints. There are still some non-local constraints that could only be satisfied on fourth or fifth rung. I'll talk about that also in my research talk. So I think there'll be another time when I can answer your questions if you have any. Right now, I'd just like to thank you for your attention.